Hi everyone. Today I'm going to be explaining the Y Combinator and how you can motivate it. So I'm inspired by this particular example in the SICP JavaScript edition, and it's an example of how you can write the factorial function without any declarations or assignments at all, right? And the reason this is interesting is because if you look at a footnote over here, we see that this is an instance of if we abstract it a bit more, we can go down a rabbit hole and discover how to motivate the Y operator. And the key essence of this is that uh, if I have a factorial function in this case, we can see that the usual way to do recursive functions is to have a name that is bound to some function body, and the function body would call itself, right? It will call the name back again. And this works in languages that have name bindings where you can bind names to certain expressions. But if we were in an interpreter like let's say lambda calculus that didn't have any name bindings, then this implementation of factorial will break down, right? Because we can't even create constant name bindings, right? So the question is, can we have recursive functions um in a in a language that doesn't support name bindings? And it turns out the answer is yes. We can actually create bindingless recursive functions using the Y Combinator. And yeah, so that's kind of what I want to motivate today. And so I guess a first checkpoint would be trying to arrive at the expression seen over here, right? So how do we arrive at this is clearly bindingless, right? There's no bindings at all. How do I arrive at a at a how do I calculate 10 factorial without any bindings? And that's what we're going to try to arrive at first, right? So that will be I think I'm going to break this video into a few parts. That will be the first part. And then the second part, I'll be trying to extend the idea and to more general functions, right? We're going to see that this implementation is very specific to factorial and it's not very human friendly, right? We cannot write this off the top of our heads. So we're gonna try to abstract away some of the complexity into something we call the Y function. I'm gonna call it Y function because it's not gonna be a combinator yet, right? I'm gonna abstract it into some function called Y, and this function y would take a simple implementation of factorial and turn it into something that you can actually use, right? So yeah, so so that'll be the second part, right? We're gonna derive the y function and see how the y function can play a role in reducing the complexity of the code that the human needs to write. And then after that, the Y function isn't a combinator yet, so we're gonna need to put in a bit more effort to turn the Y function into a Y combinator, right? So that'll be the third part, and the last part will be trying to go into a non-lazy language, right? So trying to work in a strict language and trying to make sure that Y combinator works in a strict language. That'll actually be quite simple. So before we blast ahead, let me just first, since I mentioned the word lazy, I'll take some time to to explain a bit, why we need to work in a lazy language right now, right? Otherwise, you might be wondering why I'm working in a lazy language for all this time. And the reason is because, a lazy language allows you to, have certain constructs that wouldn't otherwise be possible in a strict language. So, what is laziness in the first place? Laziness is basically, delaying evaluation of expressions until you reach a primitive function. So an example would be if I have a function that returns x plus y, right? And let's say in the function I have a side effect, which is I say adding, right? So maybe this could be some kind of logging function. And we can see that if I add display of 1 and 2 and display of 2, if I add these two things, we see something which is a bit unexpected, which might be a bit unexpected, right? We see that adding actually gets displayed first and then x and then 1 and 2, right? And this is contrary to our intuition for strictly evaluated language like source 1, right? In a strictly evaluated language, the 1 and 2 is actually evaluated first. So the arguments are actually evaluated first before they are passed into the function, right? And this is the case for strictly evaluated languages. The arguments are always evaluated and turn into values before they passed in, right? But if I work in a lazy language, then the body of the function, the arguments are actually not going to be evaluated yet until we really, really need to. And that's also why we call it lazy, right? It delays the evaluation. It's lazy to evaluate the expression until we really need to. So it doesn't evaluate this thing until it hits the plus, right? Which is a primitive function, and the primitive function is the most you can is the deepest the call stack will ever go, right? It's the highest the call stack will ever go. So you cannot recurse further into it. So when you hit a primitive function, then the evaluator is like, okay, I really, really need the values on the left hand side and right hand on the left and the right of this plus function. I really, really need the values of the two expressions I'm adding. So I'm actually going to evaluate it. So the evaluation only happens at this plus sign, right? And that's why we see this, which also means that if I comment this out, then display of one and display of two is never actually evaluated, right? It's just substituted in as this x. X is a binding to the expression, and we only see adding, and we don't see one and two, right? So this is the difference between lazy languages and strict languages. And yeah, so once again, the reason for this would I'll explain why we need this, but I'll explain why we need this in the second part, right? When I actually arrive at the expression, and then you see that the expression only works in a lazy language, but not in a strict language. Yeah, so I'll explain this when we come to it. But for now, just have a bit of trust in me that we're going to work in a lazy language and it's going to make our life easier. Okay, so moving on to part one. How do we turn? So the part one is going to be how to turn the factorial function as we understand here into something that's bindingless. And yeah, so the first thing to notice is that, okay, I'm gonna copy the factorial function like this, and I'm gonna call this maybe I'll call this bindingless factorial function, and it's gonna call bindingless factorial function like this, and this is gonna work, right? So this works, but how do we turn this into a bindingless factorial function, right? So if we're gonna remove this binding eventually, um, that means that we will never have this name in the first place, right? That means that we cannot use this name in the body of the function. So if we're going to remove the first step to making this bindingless function bindingless, right, is to make sure that the name doesn't appear in the body at all. So we're going to remove this name. And what's one way we can remove it? The best way would be to pass it in as a parameter, right? We'll be passing it in as a parameter to this bindingless factorial function. And yeah, and actually that's about it. So if I now the bindingless function, so now the bindingless factorial takes in it takes in a pair of arguments instead of just one, which means that when I call it, I need to pass in something as f, right? And the natural thing that we want to pass in as f is just bindingless function, but bindingless factorial itself, right? Because that's essentially how we achieve recursion. So if you try to pass in this, let's see if it works. No, it doesn't, right? And the reason is because now at this line, where f is going to be bindingless fact, and it's going to take in only one parameter, one argument, right? When it's a function that actually takes in two. So the very natural way to extend this is to pass in f to itself, right? And this you see works just fine. So this is great, actually. We have actually now achieved um, bindingless factorial, right? And it might still not look very convincing. So maybe if I change it up a bit, if I say constant bindingless equals to this, and I turn this into a lambda expression, then I hope that's a bit more convincing. And yeah, and this entire thing has no reference to bindingless fact, which means that I can actually take it and I can just substitute it in. So I can just take this and I substitute it in to itself, and then over here I pass in 10, and this works just fine, right? So this is actually a bindingless calculation of 10 factorial. So we have kind of achieved recursion without any bindings. This doesn't exactly match this expression here, but um, the idea is basically that so this doesn't exactly match this expression over here because the 10 is actually passed in as a solo parameter. So the simple way to achieve this is just to turn this into a giant lambda expression. Whenever you want to pull something out of the function, just need to do something like this, and this works just I need a missing bracket here. This works just fine, right? So if I take this entire thing and I call it fact, this is actually in fact a bindingless factorial function, and we are very happy, right? This is a bindingless factorial function. Once again, this is a bindingless factorial function, and we are done with the first part, right? So this proves that we can achieve uh, bindingless recursive functions, at least for the factorial function, right? And the reason why I say it's at least for the factorial function is because how do we know that this kind of works for other functions, right? In fact, this implementation is so ugly and so disgusting and so specific to the factorial function that if I told you to write a similar thing for the Fibonacci function, right? Or n choose k, right? You're gonna have a very hard time. So that brings us to the second part where we want to make the lives of our programmers easier, right? Or at least as easy as possible. And we're gonna need to step back all the way to uh our original implementation of factorial and try to start from there again, right? So this is part one. We have achieved bindingless factorial. This is part one, bindingless factorial, bindingless recursive function in bindingless recursive function. So part two, we're gonna try to derive the y function, right? So once again, what are the pitfalls of the bindingless recursive function here? It's difficult to implement yourself. And if I want to get a new, if I want to get if I want to have another recursive function like Fibonacci, you need to redefine everything here by yourself, by your own hand, right? Um, you need to redefine everything yourself, and it's tricky. So over here, we seek a simpler implementation of bindingless recursive functions, right? So how do we simplify this? And that'll be the second part. So okay, so how do we do this? Well, we can take the original function over here once again, and I'm gonna call it I'm gonna call it easy factorial because it's a easy implementation of the factorial function in a bindingless way, right? So currently easy factorial works on 10 and we are all happy and fine, right? But once again, we need to make it bindingless. So we'll do the usual step of changing this to f and this f over here, right? So okay, so this has a few this once again we're now gonna take a fork in the road. Previously, when we were at this step, the next thing that we did was pass in easy factorial over here, and we the next thing that we did was we passed in itself over here, and then we went on from there. But now before I do that, I'm actually going to do function currying on this because it turns out that later on this taking in pairs in general is not a very firstly it's not a primitive construct in lambda calculus, right? You don't really have pairs in you only have lambdas in lambda calculus, and all functions only take in one parameter. So if I want to turn this function on pairs into a function only on solo parameters, then the trick is to use currying. So I'm gonna take away the n and I'm gonna put it in as a lambda, as a parameter in over here like this, right? And that also means that now when I um that also means that now when I use this easy factorial function, I need to pass in this f, and I need to pass in some function f, right? And so what is this mysterious function that I need to pass in? We'll see what it is. I need to pass in some mysterious function f, and then it'll give me the factorial function, hopefully, which I can apply on 10, right? And so from here, we might be thinking, what function can I pass into easy factorial there will be this f that works. We can see that we need, in order to calculate, let's say, factorial of 10, right? We need this thing inside to be, this question mark, to be able to compute the factorial of 9, right? And how do we have a function that can compute factorial of 9 if we don't even have a factorial function to begin with, right? So, okay, so first of all, the question is, how do we bootstrap the easy factorial function? How do we bootstrap the factorial function from easy factorial? And the answer is that let's first consider when you have an implementation of factorial already. Suppose you have some implementation of factorial that you can treat as an oracle and you can use, then I hope it makes sense that passing in factorial into this easy factorial would make easy factorial would make this entire thing uh the factorial function as well, right? So when I look at this, it see that it works. And it's quite clear why this works, right? Because passing in factorial as f into this body means that easy factorial fact of 10, right, would call f of 9 and then multiply by 10. And f of 9 needs to compute factorial of 9 in order for the answer to make sense, right? Because 10 factorial is this f of 9 times 10, and 10 factorial, this computation is only correct if f can compute 9 factorial. And so if we pass in f to be factorial, then clearly factorial can compute 9 factorial, right? And hence, if I pass in factorial over here, we are happy, right? Because this entire thing would be a correct implementation of factorial. But clearly this is playing cheat, right? Because how can we say that we want to define factorial using factorial, right? It doesn't really make much sense. So question is, how do we bootstrap from nothing, right? How do we bootstrap without factorial? How do we bootstrap a factorial function up? um, yeah, how do we slowly build one up? And the trick is to start from the base case, right? Realize that if I have the identity function, or actually any function for that matter, right? If I have any function, um, and I pass in the identity function as f, then question is, I argue that this actually works for factorial of 0, right? And the reason is because if I pass in any function here, doesn't even need to be an identity, any function into as f, right? If I pass in 0 as n, then I'm going to hit the base case. I'm not even going to touch f, right? I'm not even going to touch f, and it doesn't matter what I pass in as f, but this expression here is correct. This expression over here uh, is a correct function for 0 factorial. So I'm going to call this fact 0, because this works for factorial up to 0, right? Up to n equals to 0. Of course, n equals to 0 is a base case, so it's not a very useful factorial function, right? If I call factorial of 0 on 0, I'm gonna see 1. But as soon as I go above 0, the answer is gonna break down, right? So how do I get something more useful from here? So if I factorial of 0, then I can actually build a function that works up to factorial of 1 by doing easy factorial and passing in factorial of 0. And this works up to 1, right? This works for factorial up to 1. This calculates factorial up to 1. And why is that the case? So we see that factorial, first of all, let's check it, right? We see that factorial of 1, in fact, can be calculated. And the reason is because I passed in factorial of 1 is easy factorial, and I pass in factorial of 0 as f, right? And if factorial of 0 here, if f can compute, because f is factorial of 0, if f can compute 0 factorial, then that means that this f over here of n minus 1 is meaningful, is the correct answer for n minus 1 equals to 0, right? If I pass in, if this f calculates 0 factorial correctly, and n minus 1 is 0, then f of n minus 1 is 0 factorial, is the correct answer, right? So this is correct. This expression is correct for n minus 1 equals to 0, right? And that corresponds to n equals to 1. And so you can see that now this entire expression is correct for n equals to 1, but it's also correct for n equals to 0, right? So this factorial function, this fact1 is correct for factorial up to 1, right? And we can repeat the same structure. So factorial 2, if I pass in fact1, then this is accurate up to 2, right? And we can double check that. That it works. And if I repeat this structure once again, then you can see that it works up to 3. Sorry. Fact 3 works up to 3. And so the key, once again, the explanation over here is that it's kind of inductive, right? It's kind of inductive. If fact of x, right? If fact underscore x works for factorial up to x, then passing in fact x into easy factorial means that this f is a function that works for factorial up to x, right? And that means that this expression, f of n minus 1, it works for factorial. It works for up to n minus 1 less than equals to x, right? And that corresponds to n less than equals to x plus 1, right? So I'm going to just type it out a bit more clearly here. If f works up to x, which then f of n minus 1 is accurate for n minus 1 less than equals x, right? And that implies that easy fact of f is accurate for n less than equals to x plus 1, right? This is just a rearrangement of this inequality over here, right? Yeah, so easy fact depends, the correctness of easy fact f depends on the correctness of fn minus 1. And if fn minus 1 is accurate for up to this bound, then easy fact f is also accurate for up to this bound. So we can see that every time I pass in the previous fact function into easy fact, I get a function that works up to one more guy, right? It is inductive, right? So that also means that if I want to call this infinity, I just need to pass in easy fact infinitely many times, and eventually the last one there's no last one, but eventually I'm gonna pass in identity, right? So how do I do this infinite recursion? I can't really specify in code, but I can use a trick, and this is where lazy evaluation also comes in important, right? So if I do an easy fact, what I pass in over here, right? I can pass in fact of infinity, right? And yeah, so this works up to infinity because if I look at this body, and I substitute in this fact in for the definition, then I substitute this thing into here, right? And then I do the same thing. I substitute this thing into here, and I do the same thing again and again, and it goes on infinitely many times. So this fact inf is actually a valid implementation of factorial, right? So if I do this, this actually works. This is actually a correct implementation of factorial. And we can check that by running factorial of 10. You can see that, oops, sorry, comment this out. You can see that in fact it works, right? So yeah, so now we actually read that we're actually halfway through part 2. We see that by infinitely applying easy fact on itself, right, infinitely many times, I actually arrive at a correct expression for f for factorial. And this is also where laziness comes in, because if I change the source, the strict evaluator, then you can see that I cannot access fact before initialization, right? And basically the reason is because I'm trying to evaluate this expression. I'm trying to evaluate this expression before I assign it to before I bind the name fact to it. And when they see this fact, they're gonna see that it doesn't exist. So that's the reason, right? But if I switch back to lazy, then this works just fine. And we're gonna so maybe thinking, wait, then isn't this kind of broken, right? It only works in a lazy irregular language. But later on, it turns out the modification needed to go to a non to a strict language is not too far off. So we're gonna stick to lazy first, and we're gonna see later that we'll handle that in part four, right? So yeah, so this works just fine, and we are very happy. Um, but there's still one more thing I'm not very happy about, which is that if I want to if I want to this still isn't satisfactory enough because I want something um I want something that can this still requires bindings, right? You can see that this still requires fact to kind of refer to itself, and eventually we this is not bindingless, right? This is a correct implementation for factorial, but not bindingless. It's not bindingless because this fact refers to this fact, and we require this fact to be a binding to have this fact here, so it's still not bindingless, right? So in the first instance, we achieve bindingless recursive function, and in this case we achieved um we achieved an easier implementation, right? We complained that the implementation here was too difficult, it's too confusing, and here we achieve I think this is a fairly simple implementation of factorial, right? I think a human can possibly do this, right? But we see that it's not bindingless. So how do we kind of merge the two and get the best of both worlds, right? And that's where part three is going to come in, right? Um, so part three, uh, Y Combinator, right? The Y Combinator is going to help us achieve that. But before that, you see that I haven't really introduced the Y function, which is what I'm going to talk about now. So we kind of want to abstract away some um we don't really like this form because this easy fact depends on this and all that. So what would be nice is we if we have a magic function y, the implementation I'll leave it bare for now. But what if this y can take in the easy factorial and produce the actual factorial function? So we want something like this, right? We want something like this. And yeah, so we want something like this where y takes in the easy factorial function and then returns you the actual factorial function that can be used to calculate stuff, right? Easy factorial is good on the eyes, right? It looks beautiful, looks very simple, but it's not usable, right? Um, but this factorial function, if I pass easy factorial into y, then it returns me a useful factorial function that can actually compute stuff. And and I'm gonna give you the implementation of y for now, and we're gonna motivate it. So it turns out the implementation of y is this funny thing over here. But how do we arrive at that? And the key observation is that what properties of what how do we arrive here? We arrive at a factorial function by applying easy factorial infinitely many times, right? And that's also known as a fixed point combinator, right? Or that's also known as fixed point, right? So drawing a parallel with math, um, if I have a constant x, x is said to be a fixed point of let's say the cosine function if and only if cosine of x equals to x, right? So if this x is a constant, so if some constant x is said to be a fixed point of this function, right? If the function applied to it doesn't change its result, right? And if you can see that if you apply cosine on both sides, the equality still stays true, and basically the cosine doesn't affect x, right? So drawing a parallel with this, we can say that the fact the factorial is a fixed point of the easy effect function, right? Because um, if I uncomment this thing, we can see that uh, fact is equals to easy fact, right? So you can see that applying easy fact on fact doesn't affect the the gives you back fact, right? It draws a parallel with this thing, right? So this is a terminology we kind of borrow from I guess like math, but this is a saying, right? This is a phrase that you'll see in some blogs and probably some academic journals. So how do we achieve so if I want so that's also why we say that the y is a function um that gives you back its fixed points, right? So y is sometimes called a a fixed point finder in some sense, right? Why this function y um if I pass in some function, it finds me the fixed point of the function I pass in, right? So factorial is the fixed point of y. In fact, I can actually rename this y to be fixed point of, right? And this would make more sense. So yeah, so how do I do that, right? So um, I guess this is kind of draws back to the inspiration from like numerical methods. Like I'm not sure if you remember some of like JC calculus where in order to find a solution, you kind of apply f in order to find the fixed point of f, you kind of apply f on it. Uh, okay, the parallel isn't very clear, but um, the parallel isn't very clear. But the point is that when I pass in okay, I'm gonna rename this back to y. But the point is that when I pass in easy factorial, I want this y. What should y do to this? The y I want y of f to be equals to f of f of f of f of f of f infinitely many times, right? And if I take one layer down like this and I replace it with y of f, you can see that this has a structure that we want, right? If I pass in a function f, I want f to be applied on y of f, which is also f of y of f. And if I expand that, then I'll get f applied infinitely many times. So reading off this definition, we see it's almost obvious why y should take the following form, right? So once again, you may be thinking, wait, this seems very weird because y still references to itself, right? And this is still not a combinator. So in fact, that would be true. This is not a combinator because it still has bindings. It still has free variables over here. This y is over here is a free variable because it doesn't appear in the parameters. All right, so this is still not a combinator, but this has the properties of the y combinator. The y combinator will eventually share the same properties over here. So this is conceptually similar to the Y Combinator, but it's not exactly the Y Combinator because strictly speaking, it's not a combinator yet, right? It's not a combinator. So passing in easy factorial gives you this thing, and we can see that this abstraction actually um is great because now if I have a function called easy feeble, and what should easy feeble take in, right? Easy feeble should take in a function f and then returns this thing. And where I want to kind of do recursion, I do it with f instead. So it takes in the parameter f, it takes in the function f, and once again, where I want in the body of the function, right, whenever I want to call itself, I'll call f instead. So easy feeble would be n maps to n less than or equal to 2. That's the base case. Um, and then the other case, the alternative would be f of n minus 1 plus f of n minus 2. All right. And now if I take this and I call y on it, then actually feeble of 10 works just fine. Right? So we can see that this y function over here is is something that allows me to convert simple implementations, right? Like easy fact or easy feeble. It allows me to convert simple implementations, right, of recursive functions into usable ones. And this is all this is easy to implement, right? This is easy to implement, at least much easier than the above over here. So now we kind of are the awkward juncture because in the first part we found a bindingless recursive function, and in the second part we found a so in the first part we found a bindingless recursive function which is too complicated. So we simplified, right? Is that this is now an easy recursive function, but now it's not bindingless, right? It requires bindings. And you see that where does it require bindings? Easy Fibo doesn't require bindings, right? Easy Fibo is free. Easy Fibo doesn't have any free variables, right? Um, but Y does have free variables. This Y in fact refers back to itself over here, right? So this Y isn't in the parameter, so Y is not a combinator yet, and we don't have completely bindingless. At least this entire thing is not bindingless, right? Because Y has a binding, right? So we're still not done yet, but now we can kind of merge the best of both worlds, right? Previously, we had a complicated bindingless recursive function, and now we have uh, something that's easy but it's not bindingless. Now let's merge the two and get a bindingless and yet easy to use recursive function. And that's what we'll cover in part 3, where the magic of the Y combinator comes in. Right? So let's return back to once again our factorial function over here. And we're gonna want to approach this slightly differently this time. Um, so we are going to want to avoid using bindings at all. So like previously, right? The first thing we want to do to avoid bindings at all is to abstract it away with this f. So passing in f as a parameter, and yeah. So now if I have fact of 10, this works just fine. But once again, oops, I need to comment out various implementations. This works just fine. But okay, let me. Okay, so we want to avoid using the pair again. So we want to avoid using the pair. Um, and one way to avoid using the pair is to have currying again. So we'll just do this, right? So this is currying again. And the one benefit of currying from this case is that previously we had f comma n minus 1. And in some sense, this f and n minus 1 was stuck together, right? Because you can't separate them apart. But with currying now, you can do this. And now this f is something that you can actually pull out, right? You can actually pull out and separate it from the n minus 1. And this is nice because this allows the right now this ff is kind of ugly to write as a user, right? It's disgusting. You do not want to write such code in you do not want a user to need to think about what f of f means, right? So we want to pull it out and abstract it away. So the natural choice to consider is to consider um is to consider a function g over here and passing in this entire thing ff. So now this thing I'm going to replace it with g, and now basically this is the same as previously, just that now this ff goes into this g and g is being substituted with ff. This is functionally the same as whatever we had previously, but now the nice thing is that this ff is outside, right? This ff is taken away from the body of the function. And what's really cool over here, at least in my opinion, is that this entire thing over here is actually our easy fibo. If you stare at it closely, this thing is actually our easy fibo, right? So yeah, so this thing is just easy fibo. Um, oops, we have oh yeah, this thing is easy fibo. And now how I use my factorial function. Okay, that wasn't how I use my factorial function is this, right? Wait, sorry. This entire thing is easy fact. Sorry, not easy fibo. This entire is easy fact, and how I use my factorial function is I pass in fact into this as f, and then I pass in the value that I want to calculate it, right? So now this expression looks really, really very neat, right? Because easy fact is something that we derive in the part 2, and easy fact is something we said that the user, the human, can derive himself, right? Easy fact is quite a nice expression. This is easy fact, and I think it's reasonable to expect that a human can write this, right? At least compared to this first monstrous first part, right? So easy fact is something the human can write. And now we have a very neat expression to turn easy fact into a factorial function, right? So, in fact, no pun intended, right? In fact, no, we can think of this as a, to make it more apparent, we can think of this as this, right? So it takes in f, and this works just fine, right? That I just turn the function into some constant binding, right? And we see that this is actually bindingless, right? Because fact over here, this fact over here is is not used anywhere inside the body of function, and this thing inside is, it has no free variables, right? The easy fact can easily be substituted from this thing, right? And this thing is bindingless, right? This thing has no free variables. So actually, fact is has no free variables. And now we are almost done because we recognize that fact, all these substitution can be done, and all these substitution can be done. So all I need to do is I can take this thing and do fact of fact, and this works, right? So all I did was substitute this constant expression into this thing, and I actually have a working bindingless easy implementation of the factorial function, right? And this entire thing is very, very close to what we want, right? So all we need to do is say that, okay, so if I abstract this away once again, then we can say that this is case. And all I need to do is look at this thing, and we recall that we want to emulate, right? We want to emulate this kind of behavior I pass in where I pass in the easy function, the easy implementation into the y, and then I get back the function that can be used to do calculations, right? So if I want to have the factorial function, I want this. So I want to say that constant fact equals to y of easy fact. So what is this y over here? I want y such that the above makes these two lines make sense, right? I want y such that these two lines are the same. So if I motivate it from this, what I can do is you realize that the final expression over here only has one instance of easy fact, right? So the natural thing we can expect is that we need to turn these two instances into just one. And I think one very common technique is to add a lambda in front of it and turn this easy fact into G, right? Basically whenever you want, basically whenever you want, oops, basically whenever you want one, two occurrences or multiple occurrences to become one, you just abstract it as a lambda expression, right? And now this easy fact goes into G, and G is substituted, G equals to easy fact is substituted into all these G's, and we get this thing. And now we are kind of basically done because we realize that this entire expression is basically our y. And this entire thing is basically our y. And this in fact works. So we have reached a magical function, this magical combinator y, that if you look at it closely, is bindingless, right? There's no free variables over here, right? There's no free variables over here, and we can and we do not need the user to write a complicated implementation of factorial anymore, right? Now we get the best of both worlds, right? In part one, the user could write a bindingless function, but it's a pain, right? And in part two, the user could write an easy function, um, and then use this y function, but the y is not bindingless. We're still kind of resorting to some kind of um, some kind of bindings, right? And in the third part, we just took a slightly different path, right, in our derivation, right? And in this path, it led us down to this expression, which has no, which uses, which has no bindings at all, right? It's actually a combinator, and on top of that, we're actually using the easy implementation that a human could have written, right? So that's amazing. We have reached the best of both worlds. And yeah, so before I end off the video, let me just clean up some things a little bit. So you can see that this y is a bit complicated, and I would like to kind of convince you that y is in fact something that satisfies this property, right? This property of y of f being equals to f of y of f, right? I'd like to convince you that this y combinator is a fixed point combinator, right? That y applied on anything um, will give you back itself, right? So how I can show that is if I simplify this y down a little bit, clean it up a little bit, you can see these matching brackets can be removed. Um, and then I can see that there's a evaluation over here. And so I'm gonna go ahead and rename some of these bindings. Um, it will make sense in a while why. So I rename the f to x, and I rename this f to y, and I'm gonna rename perhaps yeah, and I'm gonna rename yeah, actually I'm done. Right? So if we look at this expression, um we want to show our goal here is to make it very clear, very blazingly clear that y of f equals to f of y of f. Right? How do we make that clear? We can consider this expression and we can stare at it for a while. Um, and look at what happens when substitute in f, right? If I have y of f, okay, I'm gonna turn on syntax highlighting so that I can get it. Then y of f is going to be y of f is going to be this f is going to be this bound to this g, right? That means every instance of g in this body is going to be replaced with f, right? So I'm going to get x f of x, and then this evaluate is applied on y f of y, right? So this is true, and if I simplify this down a little bit more, you can see that um, there's a function evaluation here that I'm going to evaluate it. So this function, this highlighted part is going to be substituted in as x, right? And every instance of x in this expression is going to be replaced with this thing. So if I try to do that, then we see that every instance of x in this expression, every instance of x in this expression is going to be replaced with this expression. And if I do that, then we're going to see that this is going to be this applied on this. Yeah. So this is true. And if I put a bit more spacing, I hope it's really clear that okay, so I have an extra pair of brackets here, but if we look at this right now, I hope it's clear that this entire thing inside is just f of y of f again, right? This entire thing inside here is the same thing as this thing, right? So I can kind of unsubstitute it to show that this is y of f, right? And now we have in fact proven that that this fixed point combinator, this expression over here, does have the property we want, that y of f is equals to f of y of f. All right. So yeah. So with this, this is the y combinator. But the last part is going to make sure that this works in a lazy, in strict language, right? So part four, going from lazy to strict. So how do I go from lazy to strict? So if I go ahead and run this, you see it works just fine. If I pass in Fibo equals to, if I pass in easy Fibo instead, I'm gonna get the Fibo function just fine. And so now, as a user, I'm very happy because now this y is pre-declared, and anytime I want to declare a bindingless recursive function, I do not need to go through this kind of pain again, right? Now, anytime I want to declare a bindingless recursive function, I just need to think, um, I just need to think the easy Fibo, if I look at it, is a form of f, and then it maps to n, and so this is a parameter for my function, right? This is basically the body of my function, and it looks very, very similar to how I define it in a normal recursive sense, right? But just the only difference is that now your now the instead of calling itself, instead of this f being calling itself instead of this f being easy feeble, this f is just this parameter over here, right? And if my function has this structure, right? If my function has this structure, then passing it into the Y Combinator would help me turn this code into something that I can usually use to do calculations, right? So isn't that amazing? We have the best of both worlds, right? Um, we achieve bindingless functions, recursive functions, in a very easy way, right? The only complication is this y, which we took so much pain and so much blood, sweat, and tears to get through and to arrive at. But after this is done, right, all the hard work has been abstracted away for us, and now all that's left for us to do is to implement whatever function we want, and this looks so easy to implement, right? So that's the beauty of the Y Combinator. Um, yeah, and in fact, the guy who found one of the co-founders of Y Combinator, the startup accelerator, they liked this idea so beautifully, so much that they named their entire accelerator after it. And yeah, so so there's one last thing which we have to tackle, which is that if I switch this to source one, then unfortunately we hit a maximum call size, call stack. We basically had infinite recursion, and the reason is because if we stare at this a bit, the reason why this fails is because if I look at this expression, what happens is that the g. So if I consider y of some any function f, right? If as long as I pass in some function f, right, this thing is gonna be evaluated, right? In a strict language, after I pass in all the parameters, right, the body is gonna be evaluated. And and so what's the substitution gonna be like? I'm gonna substitute in this stuff into here as x, right? And it's gonna be, if I expand out the recursion, uh it's gonna be as follows. So this x is gonna be like this, and then this y thing is similar to what we did just now. It's going to be this thing, right? So it's going to be this thing, and then we're going to expand it even more. I'm going to put some spacing here to make it a bit clearer. But basically, this thing gets put into this y again, and it never stops, right? Because this y of y is causing us very big issues over here, right? This y of y, um, it gets substituted into this x, and it gets called again and again and again. And this is something that strict evaluation would try to evaluate until it's done. But in the previously we had a lazy language. In lazy evaluation, this was not an issue because it didn't do it until it hit a primitive function, which means that if I pass in a number, then it will try to evaluate it, and at some point in time, it's gonna hit the base case and stop. But in this case, if we try to evaluate it strictly in a applicative order sense, right? If it's an applicative order language, then we're gonna hit infinite recursion. And the way to kind of circumvent this is to borrow an idea from is to add a level of indirection, right? Basically, put in the laziness ourselves. And this is very similar to an idea from math called functional extensionality, where basically it's a fancy way of saying that two functions are equal if and only if f of x equals to g of x for all inputs, right? And this may seem obvious, but it turns out this is actually an axiom, right? And yeah, and I won't get into the math details over here, but we can borrow the same idea to say that if I have some function f equals to something, right? Then if I want to declare that a function that's the same, that's the exact same behavior, right? Then I can define it as follows, right? And this would g would have the same output as the f, right? For whatever you give in. But the benefit is that this g kind of delays the evaluation by a little bit, right? This g delays the evaluation of f by this thing. So So we can use this trick to look at this thing and realize that this y of y is causing us some issues. So we want to delay the evaluation of y of y, right? This y of y is giving us problems. So the one way would be to add laziness in this case. So now this z maps to y of z is functionally equal to y, right? But there's a because I add a level of indirection, I add a laziness by hand into it. Now, if I try to run this, it will not complain anymore, right? So, um, yeah. So if I try to run this now, it will not give me any problems anymore. So, okay, sorry, I need to so I need to take this tool and put it down here, and this put it down here, and we can see that in fact feeble of 10 works just fine, right? So yeah, so this is the full glory of this is the full Y Combinator in a strictly evaluated language, and we have motivated the Y Combinator from scratch, right? So yeah, I really enjoyed deriving this and motivating, and I hope you enjoyed it too, right? Yeah, it was a lot of fun, and I learned a lot. And do check out the blog, link in the description. But maybe I'll write a blog that mentions that kind of transcribe this idea when I have a bit more time. Yeah. In the meantime, um, happy programming, and I'll see you next time. Bye.